the Archimedean principle? Yes. The Archimedean principle, the quickest way to state it is to say that the natural numbers n as a set is unbounded above. So there's no such thing as a maximal element for the natural numbers, or indeed there's no such thing as even an upper bound for the natural numbers, right? Another way to think of it is no matter how high you can always count higher, right? Which seems like one of these duh statements about the natural numbers. And so how could something like this ever be useful or valuable to us in a proof context? So my job over the next few minutes is I just want to kind of explore together how a statement that's this duh can actually help us to prove something pretty deep, which is, I have to make good on a promise we made about 10 days ago, let's prove the density of the rationals within the reals. Right? So I think we can do that in just a few minutes if we arrange our thoughts carefully. So that theorem, the density theorem, says, what's the statement of the density theorem again? Density theorem says that Q is dense in R, but what does that mean?
For every interval AB that exists in R.
Okay. For every A less than B real numbers, what do we conclude? There exists a rational number x, where? In that interval. X is in the interval from A to B. In other words, A is less than X is less than B. I.e., okay. So I used a lot of abbreviations over here on the left-hand side, but that's what the density theorem says. Between any two real numbers, between any two distinct real numbers, I can find a rational number. Okay. That's what it means for Q to be dense in R. So let's see how the Archimedean principle, the Archimedean theorem, whatever we want to call it, actually is going to be the key element in a proof of this statement. So here's the picture that I want to kind of set up. Is here I've got my number line, and on my number line, I've got my two real numbers A and B. And of course I'd like to show that there is some rational number, so I'm going to use a vertical line here to denote my rational numbers and dots to represent my real numbers. So I want to show that there's a rational number that I can find, x, in between A and B. Okay. So here's how the Archimedean theorem is actually going to help us to do that. And I should start by saying this is a classic example of a proof where the first step is completely inscrutable. Okay. The first step is something that you look at and you're like, how would I ever have come up with that on my own? Okay. This is going to happen a lot. Maybe more in analysis than it does in any other subfield of math, unfortunately, which is frustrating. But one of our goals this semester is to kind of develop the intuition for how to discover those first steps of brilliance that happen at the beginning of proofs that are inscrutable to you the first time you read it. So here's how it'll work. So by the Archimedean theorem, or by Archimedes, I like saying by Archimedes because it sounds like a swear, it sounds like an oath, like by God, this is going to, by Archimedes, we can do something. And what we're going to do is we're going to say Archimedes guarantees for us that there exists a number, I'm going to call it n, that's a natural number, such that n is greater than, and here's the inscrutable part, 1 over b minus a. Okay. So first of all, you might object that 1 over b minus a is not actually a natural number, probably. Right? And I would agree with you. So there's one little hiccup in here that 1 over b minus a, because it's not a whole number, we might need to round it up in order to make it a natural number, and then use the Archimedes principle to say that there's some natural number that's even bigger than it still. But we'll assume that we can do that. So by Archimedes, there is a number n which is greater than 1 over b minus a. So Archimedes is going to let us do this. And And now it's just a matter of trying to unpack what this inequality tells us. I'm going to multiply this inequality on both sides by b minus a. Because b minus a is positive, I can keep the sense of the inequality the same. So nb minus na is greater than 1. Or maybe another way to say this is to move the na to the other side so that nb is greater than na plus 1. And so here's a little inequality. We're going to get this little inequality from, it's equivalent to our statement that we got from Archimedes. So what I'm going to do is set up an alternative number line up here, alternative copy of the reals. And in this alternative copy of the reals, we have a number nb, and we have a number na plus 1. Okay. Now, the next thing I'll do is I'll take na plus 1, which again is probably not a whole number, and I'll just round it down to the next integer, which is less than it. And I'm going to call that integer something. Let me call that integer, I'm going to call it p, let's say. And then also on my number line, I'm going to place p minus 1. And also p plus 1. I don't know whether p plus 1 is going to be here or whether it's going to be there. It doesn't really matter for our proof, so I'm just going to put it up here, p plus 1. So there are 3 consecutive integers on the number line. So p, and by integers I really mean natural numbers. That's how we're going to do this here. Okay. So there are 3 consecutive integers on the number line. Na plus 1 and nb are kind of there, and what's most important is that p is less than na plus 1. Okay. Now, if we've chosen p to be the rounding down of na plus 1 to the next nearest natural number, then if I subtract 1 from na plus 1, where is it going to land? If I subtract 1 from this number. Right, if I subtract 1, it's going to land on the opposite side of p. So in other words, na plus 1 minus 1, which is na is going to be over here somewhere. Right? It's going to be between p minus 1 and p. Okay. So now is where the magic happens. Now is when I take every one of the numbers that's on my number line here and I divide them all by n. Why would that help, first of all? Why do we think that dividing everything on that white number line there by n is actually going to give us something interesting? Right, because then we'll have a back and we'll have b back. Right? And a and b are, after all, the numbers that we're trying to figure something out about. Also, if n is a natural number, which it is, that means it's positive, and when I divide something by a positive quantity, it preserves the sense of all my inequalities. I was just telling my Math 095 students about that the other day. Divide by a positive number, your inequality remains the same. So I don't have to change the order of anything that I wrote on my number line when I divide by n. But what that does do for us is it now turns these vertical bars that we had on this line here from natural numbers into rational numbers. P minus 1 over n, and then p over n, which I'm going to kind of borrow this bar here for, and then p plus 1 over n, which we had up here, p plus 1 over n. Okay? Now what? So now that we've divided by everything by n, how do I know my proof is already done? What's my bottom picture telling me? What are we trying to produce in this proof? Right. We're trying to produce a rational number between a and b. I claim that we've done so. What is it? P over n. Exactly. And that completes the proof. So the Archimedean principle is one of these duh kind of statements, and yet if we didn't have it, we wouldn't be able to do this very first step, this very first mysterious step, right? Which gave us the inequalities that then powered the rest of the proof. But just knowing that the integers, the natural numbers, are unbounded from above was enough to get us started